And our next speaker is Meena, also from Georgia State University, speaking about investigating the origins of AGN outflows using radiative driving models in nearby Seyfert galaxies.
Hi, thank you. Can you see my screen? Can I start? Hello, everyone. Should I start? I'm sorry, just checking. Thank you. Hello, everyone. Thank you for being here today. My name is Meena, and I'm a PhD candidate at Georgia State University. Today's talk, I'm going to discuss some of the work that is part of my dissertation on investigating the origins of AGN outflows on nearby Seyfert galaxies. For those who are new to AGN outflows, I would like to give a brief introduction and provide the motivation behind my work. AGN, or active galactic nuclei, are powered by supermassive black holes that are actively feeding on their surrounding matter. This feeding process produces powerful radiation that can ionize and drive the gas away from the nucleus and create AGN winds or mass outflows. These outflows may regulate the accretion rate of supermassive black hole and at the same time influence the star formation in the nuclear regions of active galaxies by evacuating or redistributing the cold molecular gas. This control feeding and feedback mechanism due to AGN-driven outflows can explain the observed M-sigma relationship that Justin had just talked about, which shows a correlation between black hole masses and the dispersion of the velocity dispersion in the galaxy bulges. These AGN-driven outflows may also provide important parameters in various cosmological simulations. And that's why it is important to understand and constrain their origins and dynamical impact on their host environment. We usually observe these the ionized gas outflows in the strong emission lines such as O3 in the narrow line regions of active galaxies, which span from a few parsec up to kiloparsec from the supermassive black hole. On the right here is an image of a nearby Seyfert galaxy, NGC 4051, in the nuclear regions as seen in O3 emissions. Once we subtract the continuum from this image, it shows this conical structure that corresponds to the AGN-driven outflows in NGC 4051. We usually see these outflows forming this biconical structure that is shaped by the thick torus surrounding the nucleus. In the case of NGC 4051, we only see one side of the bicone, and the other side of the cone, the bicone, is hidden by the dust in the host galaxy plane. In today's talk, I will walk you through some of our recently published studies on AGN outflows in NGC 4051 and briefly discuss the overall goal of my project. So first, we use long slit spectroscopy using HST's Space Telescope Imaging Spectrograph, or STIS, and APO's Dual Imaging Spectrograph, or DIS, to obtain spatially resolved kinematics of ionized gas in the nuclear regions. And the first figure here on the left shows the large-scale image of NGC 4051 with 4 APO disk slit positions. On the right is the O3 image as shown before, with a flux contour over 3 sigma of the background flux. The two HST slits are the two HST slits are shown in the yellow, and the wide APO slits are shown in blue dashed lines. HST provides 10 times a higher angular resolution than APO, and it is excellent to observe the individual knots of emissions in the nuclear regions. However, it fails to detect the low flux emission at larger distances. And at the same time, most of the HST long slit spectroscopic observations that are available on arXiv miss majority of the outflow structure in our targets. And that's why we supplement our HST observations with APO DIS data, which provides a resolution of 1 arcsecond, but 10 times wider slits that can provide the information of the low flux information at larger distances from the central nucleus. Now, using these long slit spectra, we extract long slit data, we extract spectra along the slit and fit multiple Gaussian components to measure the velocity centroid of different kinematic components of the ionized gas. Here's an example of a spectral fit we use for the outflows in NGC 4051, where we fit the O3 and H beta emission lines together. Now, using a position velocity diagram along the slit position at position angle 188 and 233 degrees of APO data, which covers most of the outflow structure, we can derive a kinematical model for the outflows in NGC 4051. In this plot here, the gray both of these plots, the gray shaded area shows our model that matches well with the observed kinematics. The two kinematic components are shown in blue and green cross marks. We also use test data point and project them on APO slits, and the test data, because test data mostly have the clouds that are pointing towards us, while the APO slit observations shows the clouds that are along the edge of the bicone. From this model, we determine that the bicone is pointing towards us, and the redshifted side is hidden by, as I mentioned before, the dust in the host galaxy. Using the bicone model, we can also deproject the observed velocities on the galaxy frame and determine their true velocities and true distances. So once we have the kinematics, the second step of my project is to determine the stellar mass profile of the host galaxy. To do so, we use GalFit to model the surface brightness profile of the host galaxy, as my colleague Justin has already explained in details how GalFit is used. But for NGC 4051, we use the model parameters from Benz et al. 2009. And using a mass to light ratio, we converted those brightness profiles to radial mass profiles for each Cersei component, and where the Cersei components correspond to contribution from the host galaxy bulge, disk, bar, and or the nuclear cluster. And then we combine the mass from each component to get the total stellar mass distribution that is represented in this black curve on this plot. Now, once we have the radial mass distribution, we can derive the velocity profiles of the outflowing gas using an analytical model that is based on acceleration due to AGN radiation pressure and gravitational deceleration due to the mass in the host galaxy. So in this plot, the x-axis shows the distance from the nucleus, and y-axis shows the velocities of the outflowing gas. These curves shows the trajectories of the outflows in the NGC 4051. And as you can see from this plot, if you launch a cloud beyond 6 parsec, then the clouds quickly turn back to the galaxy, the host galaxy, and cannot be radially driven outwards. Some of the HST and APO observation as seen in O3 emissions, some of the O3 knots are also shown on this plot in alphabetical letters, and their location on this plot shows their deprojected or the true velocities and distances. From this plot, you can see that most of our observed clouds that are shown in this alphabetical letters are launched within 2 parsec of the from the nucleus. I would like to also mention why these findings and these results are important. So NGC 4051 hosts a low mass, low luminosity AGN, but from this plot, you can see that it can still drive the gas up to 1 kiloparsec in the host galaxy, which we have seen previously in some of our other targets in the higher luminosity AGN. But when we compare their launch distances of the outflows in NGC 4051 with those of the brighter AGN, we see a trend that shows that these launch distances of outflows increase with age and luminosities. However, we only have 4 data points so far, and that's why we need to expand our sample to find a stronger correlation. Currently, I'm working on 4 more nearby Seaford galaxies, which span over a range of age and luminosities and mass. For these targets, we have already obtained and published the spatially resolved kinematics, and for the Galfid modeling, the HST wideband images are ideal. However, I'm also using Arctic's BVRI images to obtain their color to accurately constrain their mass profile. In summary, our proposed radiative acceleration and gravitational deacceleration model can provide information of the outflows, launching sites, and the gas reservoir that could have been potentially evacuated by AGN coupling with their surrounding matter. Our initial findings suggest that these launching distances may depend on AGN luminosities, and some of these spatially resolved studies done by our own collaboration previously, mostly by Rivalsky et al., shows that the mass outflow rates in moderate to high luminosity AGN peak at hundreds of parsecs from the nucleus. So one of our goals is to compare our analytical model based on radiative driving with these mass outflow rates calculations, and to test whether the AGN radiation pressure is the primary mechanism for large-scale outflows that we see in most of our targets. Finally, we will want to determine whether these outflow sizes and launch distances scale with AGN luminosities. Although to find a stronger correlation, we need a larger sample. That's why we are eagerly waiting for Cosmos, which will provide a higher sensitivity and no contamination that would be excellent for our spatially resolved long slit spectroscopic observations. Thank you. And I'm ready for questions.
Thank you. I would also like to ask a question too. What is the redshift range of these particular targets?
So in our group, we actually work on very nearby galaxies, and the redshift shift is usually 0.5, less than 0.5. And the ones I'm working on are actually less than 0.05. Yes.
Any other questions? Oh, thank you very much. It's very interesting talk. And our next speaker is